Okay, hello everyone. Welcome to the 36th online Spintronic seminar. Thank you for joining us. This is Xinfan from University of Denver. It's my great pleasure to introduce our speaker today. Dr. Saima Siddiqui is a postdoctoral associate in Department of Materials Science and Engineering at University of Illinois at Urbana-Champaign. She completed her PhD in electrical engineering from MIT. Her research focus is to explore novel physical phenomena of electron spin in quantum materials and implement them in building Boolean and non-Boolean devices for next-generation energy-efficient computing. She has been selected as an ECS Rising Star in 2019. So without further ado, Saima, you have the floor.
Thank you, Professor Fan, for the nice introduction. And I would like to thank you and Professor Beloshensko for inviting me on the online Spintronic seminar series today. Today, I'm going to talk about artificial neural network and how the Spintronic devices can form the basic building blocks for this kind of networks. Let me first talk about what motivates the scientists and engineers all over the world to explore the neural network at the first place. Now, here I'm showing the architecture of modern computer, where the memory and the processing unit are separated from each other. And whenever the data needs to be processed, the data shuttles between the processor and the memory through this cache. Now, cache here is also another kind of storage or memory unit with a very fast access time. A huge amount of data, huge amount of processing time and energy are lost during this data shuttling process between the memory and the processor. We have this problem ever since the modern computer was invented, but we work around this problem by improving the performance of the transistor in the processing unit and by making the memories better. Today, we are in the cognitive era. We are not just happy doing the regular image processing with our computer. Rather, we want our computers to make the decisions based on this kind of image processing. In other words, we want something called artificial intelligence. For traditional image processing, an image is multiplied with a known filter. So filter here is an ensemble of weights. Filter here is an ensemble of weights, which is a matrix of R by S stored in the memory. Now, image is also a matrix of H by W. And these images are multiplied with a filter to get the output image. So both this filter and the image are stored in the memory, so they have to retrieve from the memory, and also the output image after doing the processing has to go stored in the memory. Now here we are looking into the matrices of only two-dimensional in size. However, for doing the classification, the matrices are even larger in size. They are three-dimensional matrices. And here I'm showing the operation of just one layer. And in this case, you can see that how much data we need to bring back and forth between the memory and the processing unit. So you can imagine the resistive losses in moving the data around. Since I'm here showing the single layer operation, for doing the classification with human level accuracy, we need hundreds of these layers. So we need to solve the data shuttling problem now. One way could be bringing the memory close to the processing unit so that there is less loss in the interconnect, or the best way would be doing the processing inside the memory. The system that uses this kind of matrix multiplication for classification tasks are called usually the neural network because of its similarity with the neural system in the human brain. It is also known as brain-spark computing. In today's talk, I will focus on artificial neural network. There is another neural network popular in the community is the spiking neural network, which actually mimics the operation of a brain. And if you are interested in knowing about more, there was a talk last month based on the spiking neural network presented by a postdoctoral researcher from NIST. So anyway, moving on to understand what would the best solution to solve this data shuttling issue, we need to look inside the human brain to understand the basic functionality so that we can design new devices to operate that way. Now, brain is composed of billions of units of cells called neurons. A single neuron is connected with thousands of other neurons through synapses. And these are the contacts, which are called synapses, coming from connecting one neuron to the other neurons. The synapses store the weights in the, which is something like filter of the input signal, and the input signal coming from different neurons. The cell body, which is the body of this neuron, accumulates all the data coming from different synapses, and then pass to the next neuron based on the certain threshold, which is already previously stored in the cell body. So for a brain-inspired computation, or a neural network has to do two basic operations. One is the linear operation, which is the multiplication and accumulation, and the other is nonlinear operation, which does this kind of thresholding, so that any problem converges at the end. Now, to mimic the neural activity inside the memory, what we need to create this kind of network so that the multiplication in this particular case will be the output current and the input will be the voltage, and we can store the filter elements in this memory unit. Now, this memory unit, it can be a resistor or variable resistor, so the output current is just the voltage times the conductor. Now, for doing this is something similar to the synaptic device. For doing the accumulation, the Kirchhoff's node law is very handy, so that the output current at the end is the current coming from all the different inputs. And at the end, we also need some kind of memory so that it can generate the nonlinearity functionality of the cell body. And this is the activation function generator, which we also want to replace by a memory so that we don't have to go between the processor and the memory for computation. And since it's a matrix multiplication, we need multiple of these columns. So the top part, where we have this kind of three-point cross-point architecture, this is mimicking the behavior of the synapse. And the bottom part, where we are doing the thresholding, is creating the behavior of the cell body or the neuron. Now, in today's talk, I will show you how we can use the synaptic Spintronic devices to generate the synaptic and the thresholding devices. In the first part, I will show you how we can generate analog type of device, so the resistor or the resistance or the conductance will vary in a continuous fashion. And then I will show you the digitized version of that, so that in that case, the conductances and the resistance will change in a stepwise fashion. At the end, I will talk about a system design with the analog device. I will show you the first part. So first, the analog type of device. So since we're talking about memory and the Spintronic memory, the best memory we have seen so far is the magnetic tunnel junction. And in this audience, I don't have to talk about detail of the magnetic tunnel junction. A magnetic tunnel junction, as you all know, is an ensemble of two ferromagnetic layers separated by an insulator. And it has two different resistance states, which is the parallel and anti-parallel, based on how the orientation of the two ferromagnetic layers are. And the figure of measures of the magnetic tunnel junction is represented by the tunnel magnetoresistance. Now, we have used this magnetic tunnel junction devices to create a logic device. In this particular case, we have as a free layer a continuous wire, and we put a domain wall in the free layer. So when the domain wall is on the left side of the tunnel junction, this is in the parallel state, so the output current is high, and this is represent the logic bit 1. When we apply current through this wire, then the domain wall moves on the other side of the tunnel junction because of the spin transfer torque, and now the tunnel junction is oriented anti-parallel to each other, or is the anti-parallel orientation, so that represents the bit 0 because the output current is now low. We built this device actually, and in this case, the bottom continuous wear is shaped as a semicircular arc because of the ease of applying, creating domain wall by applying magnetic field. And the magnetic tunnel junction is under this wire. So we started with the domain wall on the left of the wire, and now the magnetic tunnel junction is in the parallel case. We apply a small bias field of 30 worsted, which itself is not enough to move the domain wall. But when we apply voltage pulses to move the domain wall, it moves when the voltage is above the certain threshold. And we can measure that, and we see that sharp change in the resistance, whenever the input voltage is above the threshold. And instead of, you can think that this is a memory element because it can store the low and high, but it also operates as an OR gate, so that whenever our input is low, our output current is high. Whenever our input is high, our output current is low. Which is great that we can generate this kind of logic devices using domain wall and magnetic tunnel junction. Now the question is how that could be effective, creating this kind of, or replacing this kind of resistor where we want to vary the resistances in a continuous manner. Is it possible to replace them with this kind of devices? So first of all, we need to look at, into the detail that what are the criteria we need to fulfill. The non-volatility is already fulfilled because of this is a magnetic device. We need multiple resistance states, and we also need an input-output characteristics which varies linearly. This is particularly important if you want to keep your whole circuit for doing, say, image classification simple. And don't rely on multiple other elements to do the multiplication. So this is what we are proposing. So here, this is the same device, only the difference is now we have a longer reference layer and our domain wall is under the reference layer. So that now, when the domain wall moves, the amount of parallel region, in this case is red, and the anti-parallel region, the blue, changes continuously when the domain wall moves continuously. And the resistance will be a linear function of the position of the domain wall, and also it will be a combination of the parallel and anti-parallel resistance. And the domain wall moves linearly with the input current, because domain wall moves linearly with the input current because above a certain threshold, and so that the magnetic tunnel junction resistance will also vary linearly. And we are not the only group who thought about this kind of synaptic devices. There are other groups, and one of the important pioneering group is from Purdue, Professor Kaushik's right group. So which is great now, we have the synaptic functionality. What about the nonlinear functionality? Is this possible to generate the nonlinear function by using the similar kind of device? So in terms of requirement, the nonlinearity, we can get the, we need non-volatility. We need multiple resistance state, which we saw that it's not a problem. But the only big difference between the synaptic and the thresholding or nonlinear function generator is that it has to have nonlinear behavior, and that this behavior has to be programmable. So this is what we are proposing. If you look into the device, it's the same device, what I have shown for the synaptic device. It has a domain wall in the free layer, it has an elongated reference layer, and it is a 3-terminal device. The only difference is that now, in this case, we are, in the previous device, we relied on spin transfer torque, or we can also rely on the spin orbit torque. But in this particular device, we rely on the spin orbit torque, so that the domain wall only motion will depend on how much current goes to the bottom layer. And this spin orbit torque generator layer, we shape that in a way its width varies continuously along its length. So now if we assume an input current of I in this case, the magnetic tunnel junction will still depend on the position of the domain wall and will be represented by the combination of the parallel and anti-parallel resistance. And the one important difference is that the voltage in this case, in the previous slide I talked about, the voltage the velocity of the domain wall depends linearly with the current. It actually depends linearly with the current density. So now if you look, we can come up with a width function depending on what would be the input-output relationship. In this case, the input is the current and the output is the position of the domain wall. So there have been many analog, there have been many thresholding function has been used for the neural network, but one of the popular is Sigmoid, and I'm taking that as an example to show the functionality of our device. So from the analytical solution, we can figure out what the width of the wire would be. And from the micromagnetic simulation, we see that, yes, indeed, we can generate that kind of functionality of the input output domain wall position with the input current. But that's not where we stop. We look actually pattern our wires in that way. So in this particular case, the spin orbit torque generating a layer is the platinum. And on top, we have a ferromagnetic layer, and we're looking into the magnetoptic car microscope image. So the contrast on the wire here, the green part is the up, spin up orientation, and this yellowish part is the spin down orientation. So we have a domain wall here. And indeed, we have seen that the domain wall motion follows this kind of sigmoid type behavior with the input current. So that is, I have shown so far that using this kind of domain wall magnetic tunnel junction devices, we can create this kind of linear behavior for the synaptic devices and also the nonlinear behavior of the thresholding function generator. Before moving on, if you have any questions regarding the parts I have shown, you can ask me if you want.
At this moment, if you have any questions, you can actually just unmute yourself and directly ask the speaker.
I have a quick question, if I may.
Sure.
So I understand, maybe I misunderstood, but I think you said that the domain wall coordinate would depend on the current density. Mm-hmm. Right, but on the other hand, in the equation, you have velocity dependent on the current density. Does that mean that you need to have timed pulses to have the coordinate proportional to the current?
Yeah, you're right. So the time pulses usually in this case is always constant for the measurement. So that's how we keep that time constant, or the amount of the length of the pulse length always the same for the measurement.
Okay, thank you.
Okay, if no further question, then moving on. So let me talk about the digitized version of the synaptic and thresholding devices. So for that, we have designed a magnetic tunnel junction. Here in this case, we have a free layer on the bottom of the and we have a reference layer on the top, and it is a cobalt iron-based magnetic tunnel junction. And to make the reference layer strong enough, we have put a synthetic antiferromagnetic layer of cobalt and platinum. For the continuous film, we have measured the VSM, and we have seen that we can generate all these different kind of orientation of those magnetic layers. And this free layer actually switches with a very small field, where the synthetic antiferromagnetic layer switches with a very high field. And we also characterize our individual magnetic tunnel junction after fabricating. And we have seen that it has distinct parallel and anti-parallel resistance, and the TMR we found is about 44%. Now, in the previous slide, I have shown when you're talking about the logic device and the in-plane type of logic device, I have shown that we have created this curvature to nucleate the domain wall by using an applied field. What about how we can generate the domain walls in this kind of perpendicular magnetic tunnel junction? So now we look into this free layer more closely, and what we see that whenever we etched away the reference layer, the free layer switches with a very small field, roughly about 20%. So in this region, you have only free layer. But for the cases when we have reference layer on the top. So you can see that the dark region is the top reference layer and the light region is the bottom free wire. That region switches with high magnetic field. So now, if you look into what's the structure of this ferromagnetic layer should look like, what the domain of the ferromagnetic layer would look like, we start with a uniform free layer and the uniform reference layer. If you apply a small field, say negative 100 worsted, then the part where there is no reference layer will switch, but the part where there is reference layer on the top will not switch. So we will have a domain wall around the edges of the tunnel junction. And for measuring the resistance and looking into the functionality of our device, we have used this measurement scheme where we apply current pulses between the bottom wire, and then we measure the resistance of the wire. We apply a series of current pulses with increasing amplitude where we change the pulse width for different measurements. Then we read the resistances of the wire. And this is what our Synaptic devices for the digitized version look like. So we have a series of magnetic tunnel junction on the top, and with the application of a small bias field, we see that we can generate the domain walls on the edge of the reference layer. And these domain walls are in the free layer in the bottom. And we have created a wire where the size of the width of the wire varies linearly along the length. In this particular case, we have 200 nanometer size magnetic tunnel junction, and we gathered 9 magnetic tunnel junction together. Here the magnetic, this is the ACM images before putting the contact on top of the reference layer. So whenever we apply, since we're applying an increasing voltage along the length of the wire, because of the variation in the width, whenever we have a voltage or current amount of current going through this wire enough to remove this domain wall, the moment domain wall moves. And we can see a resistance step on our measurement. And whenever the threshold, the input current is above the threshold current of this domain wall, then we can measure the second step. And so on and so forth, we can create this kind of step function in our measurement. And the most important part is that we can fit this variation of this resistance change with the current or with the voltage pulses into a linear fit. So this is a very significant contribution for the Spintronic devices, because all the other non-volatile devices or the electronic non-volatile devices, resistive RAM or phase change memory, do not have these characteristics. And this is very important if you want to create a very simple neural network. So now we have shown that we can generate this kind of linear behavior for the synaptic functionality by using a series of magnetic tunnel junction. What about the activation function? So again, I'm using the sigmoid activation function for as an example. And in this case, also we have a series of magnetic tunnel junction, and we have domain walls on the edges of this reference layer. And we have, in this particular case, we have a wire which width is varying linearly along the length, same as the synaptic device. But the important difference is now we don't have a series of same kind of magnetic tunnel junction. Rather, we are varying the size of the magnetic tunnel junction so that we create this kind of sigmoid function. In this particular case, for reference, for simpler reference with our experimental results, I have shown you a mirrored version of the sigmoid, but it's basically the same as this one. So now you can see that this large step is coming from the big tunnel junction, and the small step are coming from the small tunnel junction. So experimentally, we have measured this magnetic tunnel junction by using the same electrical setup. And we see that indeed we can generate this kind of mirrored version of the sigmoid. And this is the mirrored function because of how we chose the reference layer when we begin with our measurement. If our reference layer were set in the opposite direction, then this will show a sigmoid instead of a mirrored sigmoid. So to summarize this part, the middle part of my talk, that I have shown you this digitized version of the synaptic and thresholding function by using the magnetic tunnel junction and domain wall in the free layer. Now the thing is, the main motivation when I started, I talked about we want to reduce the energy consumption. So where we are standing with these devices in terms of energy consumption. For a prototype device, which are in micron-sized devices, the power required to switch based on where the magnetic tunnel junction is positioned, it's about 150 microwatt to about 2 milliwatt. And we have used for this measurement, particularly this for calculation, only 8 nanosecond 8 nanosecond pulse width. So the amount of energy consumption for doing this kind of synaptic weight update is only less than 20 picojoule. And this is similar to one of the best other non-volatile memory, which is resistive RAM. But the thing is, the resistive RAM is a very skilled device. So it's not fair to compare them with our micron-sized prototype device. Now, today's industry, it's not very difficult to create magnetic tunnel junction with weight 20 nanometer and a cobalt iron wire of about 25 nanometer. Now, we have been using the parameters here I'm showing is I'm using the assumption very conservatively. So I'm thinking about using a current pulse of 8 nanosecond, but that will give us an energy consumption of the order of femtojoule. Now, to give it some perspective, the biological synapses, which is the ultimate goal, we want to be as efficient as human for classification and without consuming a lot of energy, that biological synapses is also consume about femtojoule for any synaptic weight up. Moving on to the next section, I'll talk about the system design, but with the analog kind of devices, which I have shown in the first part of my talk. So just to give you a review, that we have shown this continuous change in the magnetic tunnel junction resistance by using a domain wall under the reference layer. And by engineering the spin orbit torque generating layer, we can have this kind of nonlinear functionality or thresholding device. So the main goal is to do the multiplication and accumulation operation. So for that, our signal can be coming from, these are the input signals coming. And at the end, we sum the output current because of the conductances of the magnetic tunnel junction. And at the end of each column, we have this nonlinear thresholding function generator. But we also need to change the domain wall position because this resistors will, this resistor are a variable resistor, and to define a different weights, we need to vary the domain wall position. So we need to connect the bottom wire. So for that, we used this kind of switching, and also to separate separate the thresholding function generator, we need also switches for that. So whenever we want to change the domain wall position to having different weights, we only need to connect the switches so that we can apply the current between this SL1 and BL1 terminal for this device and SL2 and BL2 terminal to change the weight of this device. And if you want to read them, it's also possible by, again, connecting, by removing the switch and connecting only the read layer and this heat line. So this is the whole one layer I talked about where we do the multiplication for a classification task. And we have multiple of these layers. We have hundreds of these layers. So the one important thing is we can connect the next layer directly through this thresholding function. And we don't need to convert this data from the analog to the digital domain, which is what we'll do for any kind of other non-volatile devices. So this is a huge advantage in terms of energy and in terms of saving the computation time, so that the conversion doesn't take any time, and you can make this kind of neural network even faster using synaptic devices with the Spintronic, if you have the Spintronic kind of device. And in terms of architecture, it's also very simple. It has the voltage driver and the cross-point areas of the magnetic tunnel junction, and also the sense amplifier. So for the different layers, we have all this cross-point architecture for doing the multiplication and accumulation. And at the end of this, all the array there goes to this nonlinear function and go to the next layer here. And all the surrounding layers are for controlling those switches, so that we can control whether it's reading, whether it's doing the multiplication, or whether it's doing the weight up. And this architecture is similar to the resistive RAM architecture. The only difference is we are not considering any conversion between from going from one layer to the next layer. And when I'm talking about conversion, it's the conversion from the analog signal to the digital signal, and then going back to the analog signal again. The key benefit of this kind of device is that with this synaptic magnetic tunnel junction, we have shown that we have multiple of this states generation possible, and that improves the accuracy of your data when you do the classification, and the accuracy improvement is about 20%. And also, there are some variation for one magnetic tunnel junction to the other because of the fabrication error, but in the neural network, it's possible to overcome those process variation. One of the important contribution for this case is that we have this thresholding magnetic tunnel junction device, so that there is no extra overhead to storing the results, and then again, talking about the conversion, we don't have to wait for that delay, conversion delay. In terms of the CMOS device, if we think about, we have simulated a small area, which is 2 by 2, and we found out that instead of a few hundred microwatt, our magnetic tunnel junction system will only consume 10 microwatt, which is 5 times better than any other non-volatile devices. And in this case, for the simulation purpose, we considered a latency of 4 nanoseconds, which is same for all the CMOS devices and also for all the other non-volatile devices. So in future, what we are looking forward is making a system with this kind of analog synaptic devices, where the domain wall resistance, domain wall moves smoothly inside a wire, and so the resistance change is a continuous function, but it's also linear. And we want at the end of this each column a nonlinear activation function generator, also made out of this magnetic tunnel junction. And they are integrated in a continuous fashion on top of the CMOS circuitry. So they can be integrated in the back of the line of those systems, without having actually costing any area in the actual circuit. To summarize my talk today, I have shown that we can generate this analog kind of threshold function. And also we have this capability to generate the linear synaptic devices with magnetic tunnel junction and a domain wall under them. And using the similar kind of device, we also can generate a nonlinear threshold device with electrical readout. So we don't have to, in the first case where we're looking into the optical readout, in this case, we can actually integrate the system with the electrical other electrical system. And at the end, I have shown the architecture of the analog artificial neural network with magnetic domain wall and synaptic devices. Magnetic domain wall, synaptic, and thresholding devices. The talk will not be complete without the acknowledgement, obviously. So this work was done during my PhD, when I was working with Professor Mark Baldo, Caroline Ross, and Lucio, and also my colleagues who are instrumental for doing the simulation of the other non-volatile devices and the CMOS circuitry. And Asura, she was very helpful in analyzing the magnetic tunnel junction by doing the TEM. And I'd like to also thank Professor Axel Hoffman, whose support is invaluable, and a lot of numerous discussion about improving how we can present that this is the most important element, which can be very effective for showing in this neural network field. with that, I'd like to thank for attending the talk. And if you have any questions, I would be happy to answer.
Thank you very much for this very interesting talk. This talk is open for questions. If you are in Zoom, please use the raise hand option. And if you're on Twitch, just type your questions in the chat box. So let me ask the, let me ask you the first question. Actually, kind of just to follow Kirill's earlier question, it seems that you have to you keep the pulse width at 8 nanosecond.
Mm-hmm.
I guess this is when you're actually building a chip, there's a very accurate internal clock. So keeping the same duration shouldn't be a problem at all, is it?
Yeah. Yeah.
Okay.
Yeah. So
okay.
So that's one of the interesting thing for this neural network, that you don't for our particular devices we can use this small pulse width. For most of the other non-volatile devices, the pulse width is very large. So this is one of the advantages of the Spintronic devices. And you probably know we can definitely go even lower pulse width to move the domain walls.
That's what I actually want to ask. So, but to understand the first figure, that's the analog threshold device, to actually get that kind of a sigmoid curve, how it works is the width gradually actually narrows down. So as the domain wall propagates, the current density also increases. So the domain wall actually moves faster and faster. And
so yeah, that's right. So that's why. Sorry, I lost my marker. Yeah. So that's why we have this width, which is higher on the two sides, so that we can move the domain wall slower. But in the center, we want to create this ramp, which is very fast with the current density. So that's why we narrow down the width of the wire. And this is the wire of, so in this particular case is the wire only platinum, but the top where the actually domain wall is, the ferromagnetic layer, that the width of that ferromagnetic layer is constant.
Oh, okay. I see. And as you said, in principle, there can be material engineering to move the domain wall much faster. And so, for example, I think there's the recent demonstrated cobalt gadolinium just replaced with a ferromagnetic and moving even faster. So all your energy consumption and that estimation was based on platinum cobalt, is it?
So all the energy, when I'm talking about the energy consumption, those are for the digitized version of the Synaptic devices, and those are based on cobalt iron boron. So which is definitely not kind of one of the worst system, maybe in terms of domain wall motion, I would say.
I see.
Yeah.
That's good. Good to know that a lot of room to improve the energy efficiency. Thank you very much. I think Mark has a question. Mark, please go ahead and unmute.
Hi, thank you for the nice talk. It seems, so you're passing current through the Synaptic devices and then using that current to drive the neuron devices?
Okay, let me go. I'm not sure which one is that. So yeah, you're right. What I'm showing you, the whole here. So that's the idea of using this current to drive the neuron, and this, yeah.
So since the resistance changes are pretty small, do you have to amplify or detect, or how much do you have to manipulate the current in order to get it to drive the neuron?
That's a very good question. Yeah, so the amplitude change in the resistance is definitely low, and we believe it's possible to improve by engineering the magnetic tunnel junction. So we didn't actually estimate that how much current we need to drive this. But for our experiment, we know that the current requirement is for this particular is not low. It's about a few hundred microamps. So yeah, we need high current to move the domain walls there to get the functionality of the activation function generator.
Thank you.
Kirill, do you want to ask the next question?
Yeah, sure. So coming back to the question about the timed pulses. So if I understand correctly, after you perform the calculation, the domain walls stay in the new positions.
Mm-hmm.
Right? So it could potentially be both an advantage and a disadvantage. So if you want to repeat the calculation, you want to reinitialize the whole thing to reposition the domain walls in some reference position.
Mm-hmm.
But on the other hand, it may possibly be useful when you train the network in some way. In terms of different operation modes, can you comment on that? And also maybe a related question, any thoughts of how this kind of network perhaps could be trained automatically rather than, you still, for training this network, you need to use external software, right? You need to collect the outputs and then back propagate and do something like that. Is there any way to build it in the hardware?
I think, so I have shown the two different types, one, the analog version, and the digitized version. So digitized version is good in a way that I could be able to show you that I have this electrical read. So it's like you can just use these devices for the actual system. The problem with that is it's not, whenever you want to change the weights, we need to apply the magnetic field whenever we want to reset anything. Because it goes in one direction, then you have, if you want to change the resistance in the other direction, then you have to want to reset that. So we need magnetic field for that. So in that case, I would believe if we go for the analog device, then we can remove that magnetic tunnel junction requirement. So now the domain wheel stays in the same position. Which is the main thing we want, because you want the non-volatility. So you have, once you set the domain wall, and you don't want to change the weight of your device, then you don't do anything. But for training, this is something really, really one of the drawback of not only the Spintronic device, for any non-volatile device, that it still needs some external switches and external CMOS circuitry, and you cannot operate without them. And again, the advantage, you get some advantages, but you still have to worry about the peripheral circuitry and also the data movement there in the peripheral circuitry for that. So I still don't see any way whether you can get rid of all those peripheral circuitry and do all those operations just within the Spintronic device.
Yeah, but also potentially if you have a domain wall position that's controllable by current pulses, right? If you assume from the beginning that you will always be using pulses of a certain duration, then you need to initialize to the reference state. Mm-hmm. But you can possibly vary the duration and the sign of the currents in a differential way, right? If you have the derivative of your weight rather than the absolute weight, then mm-hmm. you can control that by pulses of variable duration or maybe variable magnitude of the current.
Yeah, sure. That's a great idea. One of the drawback of that is whenever you want to vary the duration of your pulse, that comes with the requirement of external circuitry, because you want now not a single clock signal, rather multiple different duty cycle of those clock signals. So yeah, it's probably some amount of compromise that what works in the best in terms of energy and in terms of the processing time.
Yeah, but the magnitude of the current is also possibly okay within some reasonable ranges, right?
Yeah, sure. I'm not worried about the magnitude of the current. I'm worried about the part where you need the extra circuitry to generate this kind of different pulses. And whenever you think about generating this different variable pulses or variable width pulses, then you also need to look into your all the filter weights, that what amount of change you have, and what which direction you want to go, and in that you also have to calculate what pulse width you have to apply.
Yeah. But you can also, I mean, imagine something like if you have a certain target output, you can compare it with a reference and feed that directly to your weights.
Sure.
And differentially control those weights.
Sure,
also.
sure.
Yeah. Okay. Thank you.
Yeah, thanks.
So I have one question from Twitch. I'll read it to you.
Sure.
I think it's by Professor Christian Benek. You mentioned switching energies of femtojoules similar to biological systems. Does that mean that energy consumption of neural networks can compete very soon with biological brains, or do the interconnects still spoil this?
That is a very good question. So whenever you create this system, you still have to, so you need a certain filter, and they have to be varied based on what data you are processing. So most of the cases, you don't have the size of the system where you can load all the filtering data at the same time, or all the inputs at the same time. So it's still, there is some limitation, and there is some data shuttling, although we are, this is when I'm talking about the change in the synaptic weight, that's comparable, but still the interconnects are involved, and so that's still is a killer factor until now. So it's not very soon that it would be comparable to the biological system, but maybe in some future.
Thank you. Do you have other questions in Zoom? Or on Twitch? Okay, it looks like we don't have any other question at this moment. So I want to thank Saima for this great talk again.